For centuries, the moon has been the astronomer's most frustrating partner. We chase its shadow across the globe, booking flights to remote islands or driving into the middle of deserts, all for a few fleeting minutes of darkness. We do this to glimpse the sun's most elusive secret, the solar corona. This ghostly halo of plasma is millions of degrees hotter than the sun's surface and holds the key to understanding the space weather that can disrupt life on Earth. But the moon is fickle. Its eclipses are rare, short, and the path of totality is incredibly narrow. But as of late 2025, that limitation has been shattered. The European Space Agency's PROBA-3 mission has fundamentally altered the landscape of solar physics. By launching 2 satellites that fly in a precise autonomous formation, humanity has created a statue in space, a giant, rigid observatory made of 2 unconnected parts held together only by light beams, sensors, and algorithms. Together, they generate an artificial solar eclipse on demand, opening a permanent window into the sun's fiery atmosphere. Today on Fun Facts Online, we are doing a deep dive into the engineering marvel that is PROBA-3, looking at how it works, why it is necessary, and what it discovered in its first historic year of operation. To understand the triumph of PROBA-3, we first have to understand the optical nightmare that is the solar corona. The corona is tenuous and faint, about 1,000,000 times dimmer than the solar disk, or the photosphere. Viewing it is, as ESA scientists describe it, like trying to see a firefly hovering next to a stadium floodlight. On Earth, the blue sky scatters sunlight, completely overwhelming the corona. During a total solar eclipse, the moon perfectly blocks the photosphere, the sky goes dark, and those pearly white streamers are revealed. But totality lasts only a few minutes. To solve this, we built space-based coronagraphs, like those on the SOHO or stereo observatories. These telescopes sit in space, removing the problem of atmospheric scattering. However, they introduce a new problem called diffraction. To block the sun, these telescopes use an internal occulting disk, a small blocker inside the telescope tube. But light behaves like a wave. It bends or diffracts around the edges of this small internal disk. This creates noise that blinds the instrument to the inner part of the corona. To avoid this stray light, traditional space coronagraphs have to over-occult, meaning they block not just the sun, but a large region around it. This leaves a critical blind spot immediately above the solar surface. Unfortunately, that blind spot is exactly where the most interesting physics happens, such as the birth of solar wind and the heating of coronal plasma. The laws of optics dictate that the only way to see this inner region without diffraction noise is to move the occulting disk much farther away from the telescope. In fact, for the specific wavelengths we need, you need the disk to be about 150 meters away from the lens. Building a continuous telescope tube that is 150 meters long is impossible for a standard satellite launch. PROBA-3's solution was radical. They decided to remove the tube entirely. PROBA-3, which stands for Project for Onboard Autonomy 3, is not a single satellite, but a binary system. It consists of 2 spacecraft. First, there is the Occulter spacecraft, a 200-kilogram satellite carrying a 1.4-meter diameter disk. Its primary job is to act as the moon. Second, there is the Coronagraph spacecraft, a 340-kilogram satellite carrying the telescope and the primary instrument, ASP-IICS. It flies in the shadow cast by the occulter. When in formation, these 2 free-flying satellites function as a single, rigid optical instrument spanning 144 meters, or roughly 472 feet. This effectively makes PROBA-3 the longest instrument ever deployed in space. Achieving this required a massive leap in spaceflight engineering known as high-precision formation flying. These satellites cannot just drift near each other. They must maintain their relative positions with millimeter-level accuracy. If the occulter drifts by just a few millimeters, the shadow misses the telescope, and the blinding sunlight destroys the image. The way the mission handles this is through a brilliant orbital strategy. The pair operates in a highly elliptical orbit around Earth, ranging from a low point or perigee of 600 kilometers out to a high point or apogee of over 60,000 kilometers. This orbit was chosen for a very specific reason. At perigee, close to Earth, gravity is strong and uneven, making precise formation flying fuel-intensive and difficult. But as the satellites climb towards apogee, they slow down, and gravitational perturbations weaken. For 6 hours during each 19.7-hour orbit, as they loop through this high apogee, the satellites enter formation mode. This is where the engineering magic happens. To keep the two spacecraft aligned, PROBA-3 uses a multi-stage system of sensors, acting like a narrowing funnel of precision. It starts with GPS and radio links. The satellites use relative navigation GPS and inter-satellite radio links to find each other and get within a few centimeters of their target positions. Once they are close, the visual sensors take over. Cameras on the coronagraph spacecraft track LEDs on the occulter spacecraft to refine the alignment further. Then come the shadow position sensors. Once the shadow falls on the coronagraph faceplate, photosensors detect the shadow's edge to ensure it is perfectly centered. Finally, for ultimate precision, they use laser metrology. A laser beam is fired between the spacecraft, allowing them to measure their relative distance and alignment to within micrometers. The control loop is entirely autonomous. The computers on board process the sensor data and fire microthrusters to correct any drift instantly. The occulter spacecraft creates the shadow, but the coronagraph spacecraft acts as the active partner in some maneuvering phases, while the occulter uses cold gas thrusters for extremely fine adjustments. This formation flying is so precise that the two separate machines behave as a single rigid structure, despite traveling at thousands of kilometers per hour. The scientific payoff for this engineering feat is the instrument ASPIICS, or the Association of Spacecraft for Polarimetric and Imaging Investigation of the Corona of the Sun. Because the occulter is 144 meters away, the diffraction fringe is minimized. ASPIICS can image the solar corona starting from just 1.1 solar radii out to about 3 solar radii. This means it can see the region just barely above the solar surface, a region that has been virtually invisible to continuous observation until now. This allows scientists to tackle 3 main objectives. First is the coronal heating mystery. The Sun's surface is about 6,000 degrees Celsius, but the corona above it soars to millions of degrees. This is counterintuitive, like walking away from a campfire and feeling it get hotter. PROBA-3 is providing the high-resolution, continuous data needed to test theories about magnetic waves, known as alpha-Gaussian waves, and nanoflares that might be transferring this energy. The second objective is solar wind acceleration. The stream of charged particles that fills the solar system starts in the inner corona. PROBA-3 observes the exact region where this wind accelerates from subsonic to supersonic speeds. Third is understanding coronal mass ejections, or CMEs. These are massive explosions of plasma that can cause geomagnetic storms on Earth. By monitoring the inner corona continuously, PROBA-3 can spot the early formation and trigger mechanisms of CMEs, improving our space weather forecasting. In addition to the main telescope, the occulter spacecraft carries DARA, a digital absolute radiometer which measures total solar irradiance, helping us track the Sun's energy output for climate models. A third instrument, 3DEES, measures energetic electron fluxes in the radiation belts, contributing to our understanding of Earth's magnetic environment. The journey to get here was a marathon. After years of development, PROBA-3 launched on December 5, 2024, aboard an ISRO PSLV-XL rocket from the Satish Dhawan Space Center in India. The launch was a textbook success, placing the duo into their initial elliptical orbit. The early months of 2025 were spent in a commissioning phase, where teams at ESA's Redu Center in Belgium carefully tested the individual systems. Then came the critical moment in March 2025 with the first attempt at formation flying. The tension was palpable. If the collision avoidance maneuvers failed, the satellites could crash. If the sensors failed, the mission would be blind. But the demonstration was flawless. The satellites locked onto each other, maintaining the 144-meter separation with the required millimeter accuracy. By June 2025, the mission achieved its first light. The resulting images were breathtaking. They showed the solar corona with a clarity previously seen only during total solar eclipses, but with a stability and duration that ground observers could only dream of. Scientists could see fine magnetic loops, streamers, and the dynamic evolution of plasma structures over hours, providing data that began rewriting textbooks almost immediately. But PROBA-3 is more than just a solar mission. It is a pathfinder. While its solar science is revolutionary, its technology demonstration is equally vital for the future of astronomy. The success of autonomous formation flying proves that we can build virtual telescopes of any size. We are no longer limited by the size of a rocket fairing. Future missions could involve huge X-ray telescopes with optics on one satellite and detectors on another kilometers away. It opens the door for exoplanet hunters using giant external star shades, similar to PROBA-3's occulter, but much larger and farther away, to block the light of distant stars and image Earth-like planets directly. It also lays the groundwork for gravitational wave detectors, like the LISA mission, which will require 3 spacecraft flying millions of kilometers apart with picometer precision. PROBA-3's control algorithms are a stepping stone to this level of mastery. As PROBA-3 continues its daily vigil, creating an eclipse every 19 hours, it stands as a testament to human ingenuity. We have not just observed nature, we have mimicked its grandest spectacles to suit our scientific needs. The artificial eclipse is no longer science fiction. It is the new standard for solar physics, illuminating the dark and violent mysteries of the star that sustains us all.